So thank you for inviting us to come. I'm Catherine Schuman. I'm a PhD student, graduating PhD student at the University of Tennessee in computer science. And I'll be going over the first half of our presentation, a programmable array of neuromorphic elements. I'll be talking about the software side, the architecture, and the algorithm side. And then Chris Saffron will be doing the second half of the presentation. He is a graduating master's student in computer engineering at the University of Tennessee. He'll be telling you about the hardware side. Our advisors are Dr. Mark Dean and Dr. Doug Birdwell at UT. And this work is supported in part by the National Science Foundation Graduate Research Fellowship Program. So the key features of our architecture are that we have very, very simple neurons. Our neurons are biologically inspired, but we're not attempting to model the biological neurons explicitly, so they're very, very simple. Our synapses implement memory with programmable delay lines. So when we talk about synapses, we're talking about the connections between neurons and our architecture. Our idea of synapses kind of encompass the idea of synapses, axons, and dendrites. A main key feature of our architecture is that we optimize the parameters and structure of our networks in both software and hardware. So rather than tying a user to a specific network structure or connectivity pattern, we instead allow the user to optimize over the structure and parameters in both the software and the hardware. Finally, our hardware is a collection of programmable elements with nearest neighbor connectivity. Chris will talk more about what the neuromorphic element looks like in the second half of the presentation. So I want to start with an overview of our architecture. Our architecture is called Neuroscience-Inspired Dynamic Architecture, or NIDA. So NIDA networks are spiking neural networks that are embedded in a three-dimensional space. They're made up of the neurons and synapses. The neurons, as I said, are extremely simple. They have two parameters, a threshold and a refractory period. They're located at the points in the three-dimensional space in the software implementation, and they're connected by our synapses. The synapses span some length in the three-dimensional space, and they have an associated delay value that's related to the length. So the longer the synapse is in the three-dimensional space, the longer the delay. That's in our software implementation. The synapses also have an associated weight value. They can be excitatory or inhibitory, and the weight values change over the course of simulation due to processes inspired by long-term potentiation and long-term depression. So the weight values change as a result of firing activity in the network. So in our software implementation, we implement the simulation using a discrete event simulation. So example events on our simulation include input events on the input neurons, change in charge events. So you can see a change in charge event on the left side of the slide there traveling along a synapse. Upon reaching the postsynaptic neuron, that change in charge event enacts a change in charge on that neuron based on the weight value of the synapse. If that change in charge causes the neuron's charge to exceed its threshold, then that will trigger a fire event on that neuron. So fire events have a couple of different behaviors in our neurons. They cause the neuron to enter a refractory period, a period following the fire during which it may not fire, but it can still accumulate charge. It also causes the neuron's charge level to return to a neutral value. It creates new change in charge events on all of the outgoing synapses, and it may also trigger those long-term potentiation, long-term depression-like processes on the incoming synapses. So you see an example of a NIDA network on the right side of the slide there. You'll notice that the neurons can exist at any point in the three-dimensional space, so there's not a fixed layered structure, and any two neurons can be connected by a synapse. So how do we determine the architecture of the network that's needed, the structure of the network that's needed to solve a particular application? We use evolutionary optimization to determine the structure of our networks. They also determine the parameters of the network. So if a user were coming in and wanted to use NIDA networks to solve their own application, there are three things that user would have to define. They'd have to define the number of input neurons for that task, the number of output neurons for that task, and a fitness function. So the input and the output neurons determine an interface to the environment for the networks. We use the input and the output neurons to form a parent population of networks. Every one of the networks in the parent population has the same input and output neurons, but we randomly initialize the hidden neurons and synapses in those networks. We then use the fitness function, that third user-defined element, to evaluate every network in the parent population. So this can be one of the more difficult things to define for the evolutionary optimization, but what it does is it associates a score value with each of the networks based on how well they're doing on the task. From there on, it's a normal evolutionary optimization. We use the scores from the fitness functions to rank them from best to worst. We use a selection algorithm like tournament selection to preferentially select better performing networks to serve as parent networks. We use a direct representation of our networks in the evolutionary optimization, although we are looking at doing indirect representations as well. We use both crossover and mutation as reproduction operators to produce child networks. And so when we have one selection and reproduction process, we have the child networks that go into the child population. We repeat the selection and reproduction process until the child population has the same number of networks as the parent population. And then we replace the parent population with the child population, and we repeat until the fitness function reaches some desired value. So we've successfully applied this optimization method and our architecture to a couple of simple applications. So this is still a relatively new architecture, so the applications are still relatively simple. We've done a pole balancing problem, a control problem. We've done the handwritten digit classification problem. We've done an anomaly detection task with potential applications in cybersecurity. We've also looked at some standard benchmark classification tasks, the Wisconsin breast cancer data set, the Pima Indian diabetes data set, and the IRIS data set. In the future, we envision applying our networks to other applications in in anomaly detection, like fraud detection and defense applications. Other applications in control, including autonomous vehicle control and brain-computer interfaces, and other classifications, including speech and video. So I want to give you a quick peek under the hood of what's going on inside these NIDA networks. So this is going to be a visualization of our NIDA network on the handwritten digit task. So what you're going to see on the left panel here is the current column of input that the network is receiving from the image. So it actually scans the image from left to right rather than reading the entire image at once. The middle panel is going to show you a network that was trained for the handwritten digit task using the evolutionary optimization. The yellow neurons are the input neurons. There's also a red neuron that's the output neuron. The network is going to rotate over the course of simulation so that you're able to see that. The other neurons are the hidden neurons in the network. You're going to be able to see the fire events as they occur and the change in charge events as they're traveling along the synapses. So this particular network was trained to recognize images of zeros. In particular, it was trained so that its output neuron would fire in the last 50 time steps of simulation if the network thinks that the image that it's looking at is a zero. So the graph on the right panel is going to show you the firing activity of the output neuron. The shaded region is the last 50 time steps. If you see a spike in the last 50 time steps, that indicates that the network thinks that the image is a zero. So here you can see it's scanning the image from left to right. It's creating the fire events on those input neurons, which are creating the change in charge events that are propagating throughout the network. The hidden neurons are becoming more visible as they become active, and so are the synapses. You can see the output neuron firing there, and for this image, it fires during the last 50 time steps, indicating a correct recognition of the digit 0. One of the things that you'll notice as these change in charge events are traveling along the synapse, many change in charge events can exist along that synapse, so our synapses are actually storing memory in these networks. So similar, same network on an image of a 5, similar activity, but it's not going to fire during the last 50 time steps of simulation, indicating that it correctly recognized that it's not a 0. Same network on the image of a 2, similar activity is going to happen. So in addition to looking like an 80s video game, this has actually given us some insight into what's going on in these networks. It's given us some insight as to how the networks are actually solving the task and what the networks look like that are being developed over the course of this evolutionary optimization. So hopefully it's given you a better understanding of how our architecture actually solves these problems as well. So now I'm going to turn it over to Chris. He is going to tell you about the hardware implementation of NIDA networks.
Okay, so a dynamic adaptive neural network array, or DANA, is one implementation of NIDA done in hardware and is currently implemented using an FPGA. A DANA is composed of a grid of elements, and each element is generic, can be a neuron, synapse, or connector, and is connected to its nearest neighbors. In the figure shown, the array, interface, and control and configuration blocks are implemented on the device with the array, and a host machine is used to communicate with the array and provides configuration data, input stimulus, and it monitors the output of the array. One advantage of this design is that while it can take up to a day to generate the array itself, different networks can be programmed onto the array on the order of milliseconds. So each DANA element is connected to its nearest neighbors, and in our current implementation, it's connected to the 16 nearest neighbors, though connector elements can be used for long-distance connections. The figure on the right side of the slide illustrates the connection scheme for a single element, and the connections overlap once they're tiled for all of the elements. So each element is connected to its 8 immediate neighbors, and is then connected to 8 additional neighbors, one layer out in the same direction as the 8 interconnections. So the choice of connecting to the 16 nearest neighbors is arbitrary and can be expanded in multiples of 8 by adding additional connections outward to other layers in the same way as the ones that skip over one connection or one element. So there are 4 major components within each generic element. The input sampling component is responsible for monitoring the state of the connected elements, and it samples them sequentially, starting with a random connection. So that random connection is chosen globally so that all elements will be sampling the same connection at the same time. The accumulate and fire component serves different purposes in a neuron and a synapse. In a neuron, it implements the neuron's threshold and charge logic and monitors for when it enters a fire state. In a synapse, it stores the weight and is used to increment or decrement the weight during potentiation and depression. The LTP-LTD component monitors the state of one programmable connected element and controls the accumulator when potentiation or depression conditions are met. Finally, the synapse delay component implements the programmable delay, which is represented as distance in NIDA, and is implemented using an addressable shift register in DANA. The figure at the bottom of the slide illustrates a gate-level schematic of a single element and illustrates the relative simplicity of our element, especially considering that it implements the functionality of both neurons and synapses. So we've implemented different arrays on several FPGAs. Using a Xilinx Vertex 7 45T FPGA, we've implemented a 16 by 16 array, though this array did not approach the maximum utilization of the FPGA. Using a 690T FPGA with 690,000 logic cells, we implemented a 50 by 50 array, which did approach the maximum utilization of the FPGA, using over 90% of the available lookup tables, and that utilization is shown in the bottom figure. Finally, using a 2000T FPGA with 2 million logic cells, we implemented an 80 by 80 array, which also approaches the maximum utilization of the FPGA, as shown in the top figure. Approximately 85% of the lookup tables are used in this design, but routing difficulties are preventing higher utilizations. So as we have implemented these arrays, we've encountered several challenges. The first major challenge is placement affecting functionality. So the placement of certain global clocking components can drastically affect the functionality of the array, can even cause it to not be functional at all. So when these components are placed near the clock source, which is near one edge of the FPGA, the tool's default placement, the array does not function at all. But when placed near the center of the array, it functions as expected. Closely related to this is the management of clocking delays. Due to the high utilization of the FPGAs, the capacitive load on these components can be very high, but the tools do not detect this. Instead, we had to manually insert additional sets of clock buffers. So for the 50 by 50 array, a single centrally located set of buffers was appropriate for the design. But for the 80 by 80, the design had to be divided into 4 regions, each with its own dedicated set of buffers. So after we inserted these new components, the tools promptly removed them during optimization. So we fixed this by placing restrictions on the modification of certain components. Finally, as we've approached the utilization limits of the FPGAs, routing congestion has been a recurring issue. We attempted to place an 85 by 85 array on an FPGA, and we were able to fit the logic of the array onto the device, but the design was not routable. So the figure on this slide shows one of the more congested regions of our 80 by 80 array. We are currently working on a mapping from NIDA to DANA. The NIDA network shown on the left side of the slide is the network trained using evolutionary optimization to be a handwritten digit recognizer. And the DANA network shown on the right is a hand-mapped conversion. There are several issues to overcome when creating this mapping, but the foremost is maintaining the same connectivity. The orange elements in the network on the right show the majority of the network is made up of connector elements to facilitate the connectivity between neurons. We may also use a similar evolutionary optimization method to come up with DANA networks directly, rather than relying on a mapping from NIDA to DANA. For our future directions, we're working on several projects. We're working on a software development kit, which will interact with DANA hardware and includes visualization and user interface components, array monitoring, programming and control functionality, and support for network libraries. We're also working on new hardware implementations. Dr. Mark Dean and I are currently creating a full custom VLSI implementation which will improve upon the density, speed, timing, and power consumption of the FPGA implementation, and will also include more advanced monitoring functionality. For this design, the process is currently available to our university. We're targeting 100,000 elements, and we plan with access to better processes to eventually reach 1 million. In the long term, we're planning on creating a mixed analog-digital device which will allow for further improvement in these areas. Finally, we are currently creating an online learning mechanism beyond LTP-LTD-like operations, which will include structural evolution. This is our team, and thank you. And do we have any questions?
Thank you for the presentation. Could you please do a compare and contrast with the NEAT algorithm?
So yeah, NEAT uses a traditional neural network, either feed forward. They also work with recurrent as well. We're doing a spiking neural network here with the evolutionary optimization, so we're encompassing that notion of delay. So our networks not only have the ability to evolve over the parameters and the structures like NEAT does, but it also evolves over the dynamics of the networks.
All right, thank you.
Thanks.
Do you have any performance figures for the MNIST data set?
Yes, so we get on the NETA application, we use an ensemble method as you might have expected from the network that only recognizes a single digit type. For that application, we have not pushed the limits of the evolutionary optimization based on our limitations at our university with the clusters that we have access to. Every network in the ensemble has been trained for about 2 hours. That being said, we achieve about 90% classification accuracy on the testing set.
Okay, thanks.